All right, let's talk about three words we throw around all the time: work, energy, and power. Seems simple, right? But in physics, well, they have these super specific and honestly kind of surprising meanings. We're going to dive right in and figure out how it's possible for all your effort to sometimes add up to absolutely zero work. So let's kick things off with a little puzzle. Picture this. You're pushing against a solid brick wall with everything you've got. An hour goes by, you're drenched in sweat, your muscles are burning. I mean, you've worked hard, right? But here's the kicker. According to physics, you've done precisely zero work. None. How on earth is that possible? Yep. See, all the confusion comes down to this big difference between everyday work and physics work. You know, in our daily lives, studying for a tough exam, worrying about something, even just holding a super heavy bag, that's all hard work. But in the world of physics, nope, none of that counts. For scientists, work is strictly about lifting, pushing, or pulling something that actually moves. Okay, so let's get into it. What does science really mean when it says work? This is the key to solving that whole wall-pushing mystery. It turns out, for work to happen in physics, there are two non-negotiable conditions, a two-part checklist. First, you gotta apply a force. Simple enough. But second, and this is the absolute deal breaker, the object has to move. It needs to be displaced in the same direction as your force. If you're missing either one of those, no work is done. So back to our wall, you applied a ton of force for sure, but displacement, zero. The wall didn't budge, and so no movement means no work. Simple as that. And there's even a simple little recipe for it. Work is something you can actually measure. You just multiply the force you used by the distance the object traveled. Force times distance. That's it. And what do we measure this in? Well, the unit is called the joule, named after the physicist James Prescott Joule. To give you an idea, 1 joule is a pretty tiny amount of work. It's roughly the effort it takes to lift a small apple about 3 feet off the ground. Not a lot, right? All right, so work needs force and it needs movement. But what do you need to even create that force to begin with? Where does that ability come from? Well, that's where our next big idea comes in: energy. You can think of it as the fuel required to do any kind of work. And the definition is actually super simple and elegant. Anything that has the ability to do work has energy. They're like two sides of the same coin. It's a transfer. When an object does work, it uses up and loses some of its energy. And the object that had work done on it, it gains that energy. And this is what really cements their connection. Since energy is literally defined as the capacity to do work, it just makes perfect sense that we measure them using the exact same unit. Yep, the joule again. Now, energy comes in all sorts of flavors: heat, light, chemical. But for what we're talking about today, let's just zero in on the two main types of what's called mechanical energy. You can think of them as the energy of motion and the energy of position. So on the one hand, you've got kinetic energy. This is the energy of motion. Anything that's moving has it. A car zooming down the highway, that's pure kinetic energy. Then, on the other hand, you have potential energy. This is stored energy. It's energy that's just waiting to be used because of an object's position or its state. Think about the massive amount of water held back by a dam, or even just a simple rubber band you've stretched out. That's potential. Let's look a little closer at kinetic energy in action. A coconut falling from a tree? That's kinetic. Water rushing through a turbine to generate electricity? Yep, kinetic. An athlete sprinting down a track? You bet. Basically, if it's moving, it has kinetic energy, and the faster it goes, or the heavier it is, the more kinetic energy it's packing. And what about potential energy? It's all about that stored capability, that, well, potential. A hammer you've raised up in the air has the potential to slam down and drive a nail. A wind-up toy car has the potential to start rolling across the floor. When you lift something up against gravity, you're giving it what's called gravitational potential energy. It's basically stored work, just waiting for you to let go. Okay, so we've got energy of motion, kinetic, and stored energy, potential. But what happens when an object goes from one state to another? Like when that hammer you're holding up finally starts to fall? Well, that question leads us to one of the most important fundamental rules in the entire universe. It's called the law of conservation of energy. And it's a simple idea, but it's incredibly profound. It says that the total amount of energy in a system never changes. It's constant. You can't create energy out of thin air, and you can't destroy it. The only thing you can do
is change it from one form to another.
Let's actually watch this happen. Imagine you're holding a ball way up high. Right now, before you let go, it's not moving, right? Its velocity is 0, so it has 0 kinetic energy. All of its energy is 100% potential energy, just stored up and ready to go. Okay, now you let it go. As it starts to fall, its height gets lower and lower, so its potential energy starts to drop. But at the same time, it's picking up speed, so its kinetic energy is rising. And if you could pause it right at the halfway point, you'd find a perfect 50-50 split. Half of its energy would be potential, and the other half would be kinetic. And then in that split second, just before it hits the ground, its height is basically 0, so its potential energy, all gone. Every last bit of that stored energy has been converted into the energy of motion. The ball is now moving at its absolute fastest, and its energy is 100% kinetic. This table kind of breaks down the math behind it. You see the mgh and all that, but honestly, don't worry about the formulas. The only thing you need to look at is that last column, the total energy one. See how the numbers for potential and kinetic energy are changing all the time? But their sum, their total, it stays exactly the same all the way down. The energy is just transformed. It's never lost. Okay, that brings us to the last piece of our puzzle, power. So, if work is about getting a job done, and energy is the ability to do that job, then power, well, power is all about how fast you get it done. Power is just the rate at which you do work. The formula is super straightforward. Power equals work divided by time. And the unit we use is the watt. Yeah, the same watt you see on light bulbs. 1 watt just means you're doing 1 joule of work every single second. Let's put this into a real-world example. Imagine 2 people, let's call them girl A and girl B, climbing the exact same rope to the exact same height. They're both doing the exact same amount of work, right? But check this out. Girl A zips up in 20 seconds, while girl B takes 50 seconds. Since girl A did the same work in way less time, her power output, as you can see on the chart, is way, way higher. So that's the key takeaway right there. Power isn't about how much work you do, it's about how fast you do it. Think about it. A really powerful car engine doesn't necessarily do more work than a weaker one over a long trip. It just does it a whole lot faster. And that brings us all the way back to where we started, pushing on that wall. We know now that you did 0 work on the wall itself, but you definitely burned energy, right? You got tired. So if energy can't be created or destroyed, where did all that energy you used up actually go? The answer is inside you. It was converted into heat by your muscles as they contracted and strained. Kinda cool, right? Something to think about the next time you're exhausted from doing what physics calls 0 work.